The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Welcome back. So today we get to sort of finish our discussion, at least the first wave of value-based methods for trying to find optimal control policies without a model. Right? So we started last time talking about these model-free methods, and just to make sure we're all synced up here. So the big picture, right, is that we're trying to learn an optimal policy, approximate optimal policy, without a model. By just learning an approximate value function. The claim is that value functions are a good thing to learn for a couple of reasons. First of all, they should describe everything you need to know about the optimal control. Second of all, they're fairly compact. I'm going to say more about that in a minute, but if you think about it, probably the value function might actually be a simpler thing to represent than the policy, a smaller thing to represent, because it's just a scalar value over all states. Okay. And the third big motivation I tried to give last time was that so these temporal difference methods, which bootstrap based on previous experience, they're like value iteration and dynamic programming, can be very efficient in terms of reusing their computation or reusing the samples that you've gotten by using estimates that you've already made of your value function to make better, fast estimates of your value function as you go. Okay. These are all going to come up again, but that's the high-level motivation for why we care about trying to learn value functions. Okay, and the first thing we did, which is really all we did last time, the first thing we had to achieve was just estimate a value function for a fixed policy. Called J pi, right? And we did it just from sample trajectories. In discrete state and action, we call them S and A, right? We take a bunch of trajectories, and you need to be able from those trajectories to try to back out J pi. And those trajectories are generated using policy pi. So I actually tried to argue that that was useful even in so if you have a robot out there that's already executing a policy, or a passive walker or something like this that doesn't have a policy, and you just want to see how well it's doing, estimate its stability, is one example, then you can actually, this might be enough for you. You might just try to evaluate how well that policy is doing. Right? We call that policy evaluation. Actually interested in is not that, right? That's just the first step. What we care about now is, given if we can estimate the value for a stationary policy, can we now do something smarter, more involved, and try to estimate, well, the optimal value function, or you might think of it as continuing to estimate the value function as we change pi towards the optimal cost, the optimal policy. Okay, we talked about a couple ways to estimate the value function for a fixed pi, right? Even for function approximation, we did first mark out chains, and then we went to function approximation. And we had convergence results for linear function approximators. And we went back and looked up, Melbourne's had a question about whether if you used lambda in your update, if it always got to the same estimate of j. I think the answer is yes, it always gets to this. The convergence proof has an error bound, and that error bound does depend on lambda, if you remember the discussion. But if you set your learning rate smaller and smaller as you go, it should converge to they should all converge to the same estimate of j pi. Okay. So if you think about it, learning j pi shouldn't involve any new machinery, right? If I'm just experiencing cost and I'm experiencing states and I'm trying to learn a function of cost to go given states, I should just be able to do a least squares function. It's just a standard function approximation task. Right? I could just do just least squares function approximation, least squares estimation. And what we call the Monte Carlo error. Just run a bunch of trials, figure out estimates of what the cost to go was at every time, and then just do least squares estimation. The machinery we developed last time was because it's actually a lot faster to use these bootstrapping algorithms. I'm glad it's much faster than that's completely. Right, so we talked about the TD algorithm, including for function approximation. Right. And the only reason we had to develop any new machinery is because we wanted to be able to essentially do that least squares estimation, but we wanted to reuse our current estimate as we build up the estimate. And that's why it's not just standard function approximation task. We developed a little bit of new machinery. Some new machinery presented it. Okay. So that's the simple policy evaluation story. Now the question is, how do we use the ability to do policy evaluation to get towards a more optimal policy? Okay. So today, given we can do policy evaluation, we want to improve the policy. The idea is the first idea you have to have very reasonable. Called policy iteration. So given I start off with some initial guess for a policy, right? And I run it for a little while. I can do policy evaluation until I'm converged on a nice estimate to get j pi 1. And now I'd like to take j pi 1, my estimate, and come up with a new pi 2. We've talked about how the value function infers a policy. And if I repeat and I do it properly, then all goes well. I should find myself if it's always increasing in performance, we can show that, then I should find myself eventually at the optimal policy and optimal value function, right? So we said TD lambda was a candidate for sitting there evaluating policy, which we've talked about a couple different ways to do policy evaluation. So the question now is, how do we do this then? That's the first question. Okay. So given your policy, given your value function, how do you compute a new policy that's at least as good as your other policy, but maybe better? Do something like a stochastic gradient. So you have to be careful with stochastic gradient to make sure it's always going down and things like that. It's a good idea. In fact, that's sort of next week's idea. Right? We combine stochastic gradient descent and evaluation to do acrocritic. But there's a simpler sort of idea. I guess it requires, I didn't even think about this when I was making the notes, but I guess it requires an observation that so the optimal value function and the optimal policy have the property that the policy is taking the fastest descent down the value function. Right? Your job is to go down the value function as fast as possible. But if you're not optimal yet, right? I've got some random policy, and I figure out my value of executing that policy. That's actually not true yet. So what I mean to say is, if you start giving your value function, you come up with a new policy which tries to be as aggressive as possible on this value function, which in our continuous sense is going down the gradient of the value function as fast as possible. Then that should be at least as good. In the case of the optimal policy, it should be the same. It should return the optimal policy again. But in the case where the value estimate is from another original policy, it should be better. Okay? So the basic story, that's the continuous thing. You want to come up with a greedy policy. That moves down, that does the best it can with this J pi. Okay? Right, so pi 2, let's say, which is a function of s, should be, for instance, getting into the discrete sense here, discrete state in action, minimize, picking the expected value, so the expected value first, and one step here, plus so I've got the cost that I incur here, plus the long-term cost here. I want to pick the new mid over A. The best thing I can do, given that estimate of the value function, right? And that's going to give me a new policy, actually, I2, which is greedy with respect to this estimate of the value function. What does that look like to you? Yeah, okay. So value iteration, or dynamic programming, is exactly policy iteration in the case where you do a sweep through your entire state space every time, and then do an update, just sweep through your entire state space, you do an update, right? Absolutely. Okay, but it's a more general idea than just value iteration. You don't have to actually evaluate all S. You might call it asynchronous value.
Shouldn't that be argument?
Oh, good, thank you. Yeah. This is argument. Catch. Yeah.
And this is like G is equal to that.
Right, I always minimize things, so G is bad. Although I don't promise that I will never make a mistake with the sign, because I try to use reinforcement notation with costs. And I can sometimes get myself into trouble. I never write R. Okay, it's always G. Okay, so, so this is the argument. The min is the value estimate in the case of value iteration. But in general, you don't have to wait till you sweep the entire state space. You can just take a single trajectory through, update your value j, or you can take lots of trajectories through and do get an improved estimate for j, and then do this and get a new policy. Right? In this policy iteration, the original idea is you should really do this policy evaluation step until your estimate of j pi converges, and then move on. But in fact, value iteration and many algorithms show that it actually is still stable even if you don't wait for it to converge. Okay. But there's a problem with what I wrote here. Hopefully there's not a technical problem, but why is that not quite what we need for today's lecture?
I just have a quick question. So if you're going to be greedy with respect to the value function that you evaluate, you can't do that with a value function because you have a model, right? So you need to.
That's actually exactly that. You answered the question I was asking. That's perfect. Right? So the problem is I said model free, but then I wrote down a model here, right? So how can I do, even in the steepest descent or continuous sense, right, that this is sort of, in the discrete sense, argument over A is typically done with a search over all actions. In the continuous state in action, I think it was finding the gradient down the slope. Okay? But right, both of those require a model to actually do that policy. So the first question for today is how do we come up with our greedy policy, basically, without having a model? It's maybe a funny way to say it, if people know this, but that's the. What do you think? People who haven't read all the RL books, what do you think? What's the, how could I possibly come up with a new policy without having a model? Good. You could sample. You could start. You could do some local search to come up with that. It turns out, I didn't actually ask the question in a way that anybody would have answered it the way I wanted. So it turns out if we change the thing we store just a little bit, okay, then it turns out to become trivial to do model-free greedy policy. Okay, so the way we do that is with Q functions, right? We define a Q function. It's a lot like a value function, okay, but now it's a function of state and action. So what's a Q function? A Q function is the cost you should expect to incur given you're in a current state and you take a particular action. Right? So it's a lot like a value function, but now you're actually learning a function over both state and actions. So in any state, Q pi is the cost I should expect to incur given I take action A for one step and I follow policy pi for the rest of the time. Make sense? Right, so I could have my Acrobat controller or something like this, and in the current state, I've got a policy that mostly gets me up, but I'm learning more than just what that policy would do from this state. I'm learning what that policy would have done if I, for one step, executed any random action, or a function for any random action, and then what would I do from the, given I ran that controller for the rest of it. Okay, algebraically, it's going to make a lot of sense why we store this, but it's actually interesting to think a little bit about what that Q function should look like. And if you have a Q function, you certainly can also get the accounting function. Right, because you can look up for a given pi what action that policy would have taken. You can always pull out your current value function from Q. But you can also create a simple relationship here with the opposite. Oops, see, I almost didn't remember any. And for the optimal cost to go, I just have to do that search over rate. I almost forgot. You can give your job for the day. Make sure I don't flip any signs. Okay, we're roboticists in this room. What does it mean to learn a Q function? What are the implications of learning a Q function, right? Well, I guess I didn't say, so given the Q function, pi s is trivial now. Having a Q function makes action selection easy. Pi 2 of s is now just a min over a Q pi s and a, right? Where Q pi was designed with pi 1. If I was willing to, the reason to learn a Q function in one case here is that it tells me about the other actions I could have taken. Right? And if I want to now improve my policy, then I'll just look at my Q function at every state I'm in. Instead of taking the one at pi a, I'll go ahead and take the best one. Right? If pi 1 was optimal, then I'll just get back the same policy. But if pi 1 wasn't optimal, then I'll get back something better, given my current estimate of Q. Okay. Well, what does it mean to learn Q? And this is actually all you need to learn to do model-free value learning to an optimal policy. That's actually really big. Okay? So, it's a little bit more to learn than learning a value function, right? So, we're learning about your robot here. Right? If I had to learn J pi, how big is that? If I'm going to say I've got n-dimensional states m-dimensional U. Just think about the continuous case even though I'm doing this. If I have to learn J pi, how big is that? What's that function mapping from? It's learning a scalar function over the state space to R1. Right? It's just really a scalar function. If I was learning a policy, how big would that be? Right? If I was learning a stationary policy, that might be that. So how bad is it to learn Q? What's Q? Let's keep a deterministic policy for now. Yeah. Now I've suddenly got to learn something over. Sorry, I can pause that. Yeah. Okay. And for grins, what would it be to learn a model system? If I wanted to use this idea, what's that model? Yeah, right. So F, and then N plus M to R N. Okay. So let's just think about how much you have to learn. So the easiness of learning this is not only related to the size, but it does matter. Okay. So most of the time as control guys, as robotics guys, we would probably try to learn a model first, right? And then do model-based control. The last few days we've been saying, let's try to do some base-bound learning model. Here's one interesting reason why. It's actually, learning a model is sort of a tall order. It's a lot to learn, right? You got to learn from every possible state in action. What's my, X dot? Or this is only learning from every possible state in action. What's the expected cost to go taking that? Learning to scale it. Okay. So it's learning one out of all that. And the beautiful thing about optimal control, with this sort of additive cost functions and everything like that, the beautiful thing is that this is all you need to know to make optimal decisions. You don't need to know your model. That model is extra information. All you need to know to make optimal decisions, given these additive cost function forms, is given I'm in a state in a given action, how much do I expect to incur cost? It's a beautiful thing. Okay. So if we make it stochastic, it gets even sort of, learning a stochastic model, if your dynamics are variable and that's important, you want to do stochastic optimal control, learning a stochastic model is probably even harder than that. Right? Maybe I have to learn the mean of x dot plus the covariance matrix of x dot or something like this. Right? Learning a stochastic model would be even more expensive. Q, in the Q sense, I left it off in the first pass just to keep it clean, but Q is just going to be the expected value around this. Okay. So Q is always going to be a scale, even in a stochastic and optimal control sense. So maybe this is the biggest point of optimal control, honestly. Optimal control related to learning is that if you're willing to do these additive expected value optimization problems, which I think we've seen lots of interesting problems that fall into that category, then all you need to know to make decisions is to be able to, the value function, the Q function here. Right? The expected value of future penalties. You throw everything else away, doesn't matter. Okay? Important point. Just to soften it a little bit, in practice, that you might not get away with really that, right? If you have to somehow build an observer to do state estimation or to estimate Q, or you've got, there might be other reasons floating around in your robot that might require you to learn this. Okay, but in a pure sense, that's really what you need to know. Okay. Yeah.
Did you put X and U? Should that be S and?
Right. We could have I could have said n is the number of states.
I just meant it should be S and A.
Right, I didn't write, I wrote the dimension of x, and I called it r, n, and m. That's what I meant. If you want to make an analogy back here, that it would actually be just the number of elements in S and A. But I wanted to sort of be roboticist together for a little bit.
Okay. This is just the computer scientists that did this really.
But it does make things easier, so I still do. Okay, so I meant to do x. Okay, so that's my effort. Okay, so now, how do we learn Q? I told you how to learn J. Q looks pretty close to J. How do I learn Q? I told you about temporal difference learning. Probably wouldn't have wasted your time talking about temporal difference learning if it wasn't also relevant for what we needed to do these model-free value methods. So let's just see that temporal difference learning also works for learning these functions. Great, not too surprising. Let's do just the simple case first, where I'm just doing, remember TD0 was just bootstrapping. It wasn't carrying around long-term rewards. It was just saying, I'm going to do one step, and I'm going to use my value estimate for the rest of the time as my new update. Okay? And I'll go ahead, since we talked about last time how the function approximator case can reduce to the Markov chain case. Let's just do it like, let's say Q prime of S is alpha I, PI, and linear function approximators, or in the vector case, alpha T, B, let's say. Okay, then the TD lambda update is going to be, TD 0 update is just going to be alpha plus gamma. Call it half just to be careful here. Pi. S. These really are supposed to be SNs, and I get along a set pattern, but I'm sloppy about it, so. Okay. And Q pi, or the gradient here in the linear function approximator case is just pi S. Okay. So if you look back in your notes, that's exactly what we had before, where this used to be J, right? We're going to use as our new update, we're going to say that our new estimate for J is basically the one-step cost plus the long-term look-ahead. AN plus 1 in the case of doing on-policy, if I'm just trying to do policy evaluation, is going to be pi. We'll use that one-step prediction minus my current prediction. I'm going to try to make that go to 0. And in order to do it in a function approximator sense, that means multiplying that error, the temporal difference error, by your gradient. And that does something like gradients on your temporal difference cost. But not exactly, because it's this whole recursive dependence thing. People get why. People get that it's not quite gradient descent, but like this. This looks a lot like what I would get if I was trying to do gradient descent on something, right? But only in the case of TD1 is it actually gradient descent. But normally, if I have a y minus f of x, I'm trying to do the gradient with respect to this. I'm going to minimize this. something, if I take the gradient with respect to alpha, I get that error, alpha x. Which is what we've got here. This is our error. If we assume that this is just my desired, and this is my actual, then this is gradient descent. But it's not quite that because this depends on alpha. These all depend on alpha. So by virtue of having this one in the alpha, it's not exactly a gradient descent algorithm. But it still works. People prove that it works. Is that okay? And actually, in the case where TD is 1, these things actually go through and cancel each other out to the point where it is a gradient descent algorithm again. But I want you to see, this is my error. I'm trying to make Q at my current state in action look like my one-step cost plus Q of my next state in action. And I'm going to do that by multiplying my error by my gradient. And the gradient is then kind of idea. Okay, you can still do TD lambda if you like also on Q functions. And the big idea there was to use an eligibility trace, which in the function approximator case was gamma lambda EIN plus my gradient. Okay, and then my update is same thing. This is my big temporal difference here. And instead of multiplying by the gradient, eligibility trace. And magically, through an algebraic trick, that remembering the gradient computes the bootstrapping case when lambda is 0, the Monte Carlo case when lambda is 1, and something in between when lambda is 0. Okay, so you can still do temporal difference there. Big point number 2. Big idea number 1 is we have to use Q functions to do action selection. Big point number 2. Is off policy evaluation. So once we start using Q, we do this trick that I mentioned the first day we were doing value methods, and that is to execute policy pi 1, but learn Q pi 2. Can you see how we do that? By virtue of having this extra dimension, we know we're learning, bless you, not only what happens when I take policy pi from state S, I'm learning what happens if I take any action from state S. Okay? That gives me a lot more power. Because for instance, when I'm making my temporal difference error, right, I don't need to necessarily use my one-step prediction as the current policy. Right? I can just look up what would policy 2 have done. makes sense. Because I'm storing every state action pair. It's more to learn, it's more work, but it means I can say, I'd like my new QPi2 to be the one-step cost I got from taking A, plus the long-term cost of taking policy I2. And then all the same equations play out, and you get an estimate for policy 2.
Does it count like,
Yeah.
does it count more than the first step of policy 2 and then like take the cost to go with policy 1, or does it somehow?
So I can't switch, well, we'll talk about whether you can switch halfway through. But once, if I commit to learning QPi2, right, then actually this whole thing is built up of experience of executing policies 2, even though I've only generated sample paths with policy 1. Okay, so it's a completely consistent estimator of QPi2. Right? If I halfway through decided I wanted to start evaluating Pi3, then I'm going to have to wait for those to cancel out or play some tricks to do that. But it actually recursively builds up to be an estimator of Pi2.
Can I ask a question?
Of course.
If you have that topic right over there, and you want to give as a function like that, we can substitute y.
You talk about this? Okay.
We can substitute y by g plus gamma next g, right?
Yeah.
And then take the derivative.
Yes.
Why don't we do that?
So why isn't it true gradient descent? That's exactly what I proposed you do, but the only problem is this isn't what we have, right? What we actually have is this, right? Which means this is not the true gradient. I'd also have a term for partial y partial.
So that's what I'm suggesting, so instead of y alpha, we can actually put g plus gamma, the approximation of y. So this g plus gamma q is a better approximation for y, right? So we can put
I'm trying to perfectly make the analogy that this looks like that, and this looks like that. Okay.
Right, but when you're taking the derivative from that function, we assume y is constant,
Yes.
and then solve it.
Yes.
We can actually assume that y is dependent on alpha.
Yeah.
And the derivative of that term with respect to alpha as well.
Yeah.
And then solve it.
Yes. So you could do that. Okay. So you're saying why don't we actually have a different update which has the gradient of that? Okay. Good. So in the case of TD0, TD1, you actually do have that. And I think what's true, I worked this out a number of years ago, but I think it's true that if you start including that, if you look at the sum over a chain, for this standard update with TD, not the TD0 for instance, that those terms, this term now will actually cancel itself out in this term here, for instance. It doesn't work. It doesn't work nicely. It gives you back the Monte Carlo error, right? It doesn't do template. It doesn't do the bootstrap. So basically, if you start including that, then you do get a least squares algorithm, of course, but it's effectively doing Monte Carlo. Okay? You have to sort of ignore that to do the template difference. Right? You're actually saying, I'm going to believe this estimate in order to do that. Okay? Temporal difference, if you actually want to prove any of these things, I have one example of it in the note. I think that I put in TD1 is gradient descent in the notes, just so you see an example. The rule of the game in temporal difference sorting derivations and proofs is you start expanding these sums, and terms from time n and terms from time n plus 1 cancel each other out in a major way, and you're left with something much more compact. That's why we call it algebraic trick, why these things work. Okay? But because these are not random samples drawn one at a time, they're actually trajectories which relate to each other, that's why it makes it more complicated. Okay, so we said off policy evaluation says execute policy pi 1 to get pi 1 generates SN, AN trajectories. Right? but you're going to do the update alpha alpha plus the just write it quickly here GSA plus gamma q pi. It's going to be an estimator of q pi 2 Sn plus 1 pi 2. What would pi 2 have done? Kind of Sn plus 1. In general, multiply by eligible metrics. Okay. All right, so that's a good trick. That's a really, really nice trick. Let's learn about policy 1 or policy 2 while we execute policy 1. Okay, so what policy 2 should we learn about? Again, these are I'm asking the questions in bizarre ways, and there's a specific answer, but I don't know a better way to ask that question. Our ultimate goal is to not to learn about some arbitrary pi 2. I want to learn about the optimal policy, right? I don't have the optimal policy, but I have an estimate of it. So actually a perfectly reasonable update to do, and the way you might describe it is, let's execute, I'm putting it in quotes because it's not entirely accurate, but it's the right idea. Execute policy 1, but learn about the optimal policy. Okay? And how we can do that? Well, shorthanded Q star here. Estimated Q star is Sn plus 1. That makes total sense. Might as well, as I'm learning, always try to learn about the policy, which is optimal with respect to my current estimate, J hat. And this algorithm is called Q-learning. Okay. It's the crown jewel of the value-based methods. I would say it was the gold standard until probably about 90, something like that. When people started doing policy grading and stuff more often. Okay. Even probably halfway through the 90s, people were still mostly writing papers about Q-learning. And there was a move to do policy grading.
So is your current estimate of Q star not based on pi 1?
It is based on data from pi 1. But if I always make my update, making this update, then it really is learning about pi 2.
Isn't pi 2 what you're computing with this update?
Okay, good. So there's a couple ways that I can do this. So in the simple policy iteration, you evaluate for a long time, and then you make an update. You evaluate for a long time, you make an update.
This is dynamic.
This is always sort of updating, right? That's the right. And you can prove that it's still a sound algorithm despite doing that. But yes, this is always sort of updating its policy as it goes. Compared to this, which is more of the learn about pi 2 for a while, stop. Pi 3 for a while, stop. This is trying to go straight through pi. So Okay, good. So what is it, what's required for a Q-learning type algorithm to converge? So if even for this algorithm to converge, in order for pi 1 to really teach me everything there is to know about pi 2, there's some important feature, which is that pi 1 and pi 2 had better pick the same actions with some low probability. Okay. So off policy works. Let's just even think about, I'll even restrict my discussion first in the discrete state and discrete actions in the Markov, the MDP formulations. Off policy works if pi 1 takes, in general, all state action pairs with some small probability. Right, if pi 2 took action 3 in state 1 and pi 1 never did, and there's no way I'm going to learn really what pi 2 is all about. I don't think that sentence actually contributes. Okay, so how do you do that? If you're thinking about greedy policies on a robot, if you've got your current estimate of the value, and you do the most aggressive action on the acrobat, I'll tell you what's going to happen. You're going to visit the states near the bottom when you start learning a lot, right? And you're never going to visit the states up at the top, right? When you learn. So how are you going to get around that on the acrobat? On the acrobat, it's tough, actually, right? But the idea is you better add some randomness, right? So that you explore more and more state and actions. And the hope is that if you add enough for a long enough time, you're going to learn better and better policies, and you're going to find your way up to the top. Right? So the acrobat is actually almost as hard as it gets with these things, right? Where you really have to find your way into this region to learn about the region. In fact, my beef with the reinforcement learning community is that they learn only to swing up to some threshold. They never actually balance at the top. If you look at, there's lots of papers, countless papers written about reinforcement learning, Q learning for the acrobat and things like this, and they never actually solve the problem. You just try to develop QR at the top, but they don't do it. They just get up this high. Because it is sort of a tough case. So how do you do it? So you add, like I said, in order to start exploring that space, you better add some randomness. So one of the standard approaches is these epsilon greedy algorithms. So I said, let's make pi 2 exactly the minimizing thing. That's true, but if you execute that, you're probably going to get stuck in it, right? Much better to execute a policy by S, where let's say the policy I care about, I'm going to execute with probability, sort of flip a coin if pull a random number between 0 and 1. If it's greater than epsilon, then go ahead and execute the policy you're trying to learn about, but execute some random action. Otherwise. Okay, so every time every DT, I'm going to flip a coin. If it, well, not a coin, 100-sided coin. 100 to 0 to 1, a continuous thing. If it comes out less than epsilon, I'm going to do a random action. Just forget about my current policy. Pick a random action. The uniform distribution over actions. Otherwise, I'll take the action from my policy. Okay? And by virtue of having this off policy learning things, I can still learn about pi 2 even if I'm taking this pi epsilon. Right? But I have the advantage of exploring all the state actions. Good. I'm missing
Is that the most randomness you can produce and still have it converge?
There's a couple different candidates. The softmax is another one that people use a lot. And a lot of people, I mean, in the off-policy sense, it's actually quite robust, right? So a lot of people will talk about using behavioral policy, which is just sort of something that's designed to explore the state space. Actually, my candidate for behavioral policy would be something like an RRT, right? We should really try to do something that gets me into all areas of state space, for instance. And then maybe that's a good way to design, to sample these state action pairs. And all the while you try to learn about Pi2. So it is robust in that sense. When I say works here, I have to be a little careful. This is only for the MVP case that's really guaranteed to work. There's more recent work doing off-policy and function approximators. And you can do that. I don't want to bury you guys with random detail, but you can do off-policy with linear function approximators safely. Using an importance sampling regime. That's worked by doing a pre-count. The basic idea is you have to, if your policy is changing, like these things, if it's changing over time, you better weight your updates based on the relative.
But I see that that's.
But what you're learning about is the state, the probability of taking this action for one step and then executing Pi2, and that's still well defined. Even Pi2 will never take that action.
Oh, yeah, that's,
So I think it's good. The thing that has to happen is that Pi2 has to be well defined for every possible state.
okay, so the key thing with QPi2 is take a certain, from a certain state, take a certain action, then execute Pi2.
Yes.
Okay, sorry, I lost that definition.
Okay, good. Sorry.
I'm trying to clarify.
Yes, so cool. So I think that still works. Okay. So this is good. So let me tell you where you are so far. So we've now switched from doing temporal difference learning on value functions to temporal difference learning on Q functions. And the major thing we got out of that was that we can do this off-policy learning. Right? You put it all together back into my policy iteration diagram. And what we have, we defined the policy evaluation, that's the TD lambda. We define now our update, which could be this in the general sense. This one is, if I used Pi1 again, if I really did on policy, if I used Pi1 everywhere, while I'm executing Pi1, then this would be called SARSA. On policy Q learning, on policy updating. And Q learning is this, where you use the min over 8. And what we know, that people have proven, the algorithms were in use for years and years and years before it was actually proven that they converge, even in the tabular case, where you have finite state actions. But now we know that this thing is guaranteed to converge to the optimal policy. That policy iteration, even if it's updated on every step, is going to converge to the optimal policy and the optimal Q function, given that all state action pairs are busy in the tabular case. Okay. If we go to function approximation, if you just do policy evaluation but not update, then we have an example where this is actually in 02 or something like that, maybe 01 or 02. Maybe 01. 2001. We finally proved that off policy with linear function approximation would converge when the policy is not changing. Okay. No control. So the thing I need to give you before we consider this a complete story here is, can we do off-policy learning? Right? Can we do our policy improvement update stably with function approximation? Okay. And the algorithm we have for that is our least squares policy iteration. Remember least squares temporal difference limit? Right. Sort of. The idea was that if we look at the stationary update, maybe I should write that again. If I look at the stationary update, if I were to run an entire batch of, I mean, the big idea in doing the least squares is that we're going to try to reuse old data. We're not going to just make a single update and spit it out, throw it away. We're going to remember a bunch of old state action pairs and try to make a least squares update, which does the same thing as temporal difference learning. In the Monte Carlo sense, it's easy, it's just function approximation. But with this TD term floating around, it's harder. So we have to come up with least squares temporal difference learning. And in the LSTD case, the story was we could build up a matrix using something that would look like phi of S gamma phi transpose. This is I k. We will just write I k here. I k plus 1 minus phi k. Times my parameter vector and b sum of these terms e, which were b of I k times our reward. And if I did this least square solution, or I can invert that carefully with SVD or something like that, then what I get out is the jumps immediately to the steady state solution of TD lambda. So this is essentially the big piece of the TD lambda update, broken into the part that depends on alpha, the part that doesn't depend on alpha. I could write my batch TD lambda update as alpha equals alpha plus gamma A alpha plus B, and I can solve for that at steady state beings. All right, so least squares policy, least squares temporal difference learning is about reusing lots of trajectories to make a single update that was going to jump right to the case where the temporal difference learning would have gotten through if you just replayed it a bunch of times. Now the question is, the policy is going to be moving while we're doing this. So how can we do this sort of least squares method to do a policy iteration? Again, the trick is pretty simple. Learning, we're just got to learn the Q function instead. That's the biggest trick. Okay. So in order to do control, not just evaluate a single policy, but actually try to find the optimal policy, first thing we have to do is figure out how to do LSTD on a Q function, okay? And it turns out, it's no harder. Yeah, what's up? Any acronyms? It turns out if you keep along a matrix in exactly the same form as we did in least squares temporal difference learning, but now we do everything with functions of S and T. Exact form of the update really doesn't matter too much. I just want you to know the idea here. Alright, gamma is A inverse B. This whole time we're representing our Q function. Our Q hat, S A is now linear combination of nonlinear basis functions on S and A. I tried to put a transpose with my poorly throughout everything. So you're saying this one of these shouldn't be transposed? Yeah. Good. So I might have flipped. You're right. This one. I wrote this whole update as the transpose of the other, of what I just wrote over here.
So maybe this makes like alpha, no different than goes A plus B, some stuff.
Yep, and there's an alpha. Sorry. Thank you. Well, actually, it's the alpha is really not there. It's I should write here. It's A times alpha is what makes the update. So we get rid of alpha. Yeah, so that is actually this is the one I did. Okay, good. So it turns out you can learn a Q function just like you can learn a value function with storing up these matrices, which are what TD learning would have done in a bash sense. Okay. And then just making a one-step shot to get directly to the solution for temporal difference learning for the Q function. And again, I put in here S prime. And I left this a little bit ambiguous. So I can evaluate any policy by just putting in that policy in here and doing the replay. And it turns out, if I now do this in a policy iteration sense, LSPI, least first policy iteration. Basically, we start off with an initial guess. We do LSTDQ to get Q pi, and then you repeat. Yeah. Then this thing, that's enough to get you to it converges. Be careful about how it converges. It converges with some error bound. To Y star, Q star. Okay. The error bound depends on a couple of the parameters. So technically it could get close to your solution and oscillate or something like that. But it's a pretty strong convergence result for these four policy improvement with a value, with approximate value function. Okay. In the pure sense, it is, you should run this for a while until you get a good estimate through LSTD and then you get to your new Q pi. But by virtue of using Q functions, when you do switch to your new policy, pi 2, let's say, you don't have to throw away all your old data. You just take your old tapes and actually regenerate A and B as if you had played out those old tapes, as if you had seen the old tapes executing the new policy. And you can reuse all your old data and make an efficient update to get Q pi in the second step. Okay. Least squares policy configuration. Too simple. Okay, I know that was a little dry and a little bit and a lot, but let's make sure we know how we got where we got. So there's another route besides policy, pure policy search to do model-free learning. All you have to do is take a bunch of trajectories, okay, learn a value function from those trajectories. That's when you don't even actually have to take the perfect, your best controller yet. You can take some RRT controller, something that's going to explore the space. You try to learn about your value function, okay? Learn Q pi. Through these LSTD algorithms, you can do a pretty efficient update for doing Q pi. You can improve it efficiently by just looking over at the min over Q, and pretty quickly iterate to an optimal policy and optimal value function. The only thing you have to store in that whole process is the Q function. And in the LSTD case, you remember the history of tapes just so you can use them more efficiently. Okay? Yeah.
So could you use this on the flapper that John showed? Or so what's the...
Good. Very good question. So that's an excellent question. So in fact, the last day of class, what we're going to do is going to, the last day I presented in class, I'm going to go through a couple of sort of case studies of different problems where people have had success and tell you why we picked the algorithm we picked, things like that. So why didn't we do this on the flapper? The simplest reason is that we don't know the state space. It's infinite dimensional in general. So that would have been a big thing to represent a Q function for. It doesn't make it invalid. We could have tried to approximate the state space with even a handful of features, learned a very approximate Q function, and done something like actor critic like we're going to do next time. But I think in cases where you don't know the state space, or the state space is very, very large, and you can write a simple controller, then it makes more sense to parameterize the policy. It really goes down to that game, the accounting game, in some ways, of how many dimensions things are. But in the fluids case, you could have a pretty simple policy from sensors to actions, which we could twiddle. We couldn't have an efficient value function. Now, there are other cases where the opposite is true. The opposite is true, where you have a small state space, let's say, but the resulting policy would require a lot of features to parameterize. Right? But I think in general, the strength of these algorithms is that they are efficient with reusing data. The weakness is that, well, the weakness a few years ago would have been that they blow up all the time, but algorithms have gotten better to the point where we have some convergence guarantees. Not the general thing. I never told you that it converges if you have a nonlinear function approximator. We'd love to have that result. We don't have it. Maybe we won't have it for a while. But if you, in linear function approximation sense, we have those. But there's a lot of success stories with this. These are the kind of algorithms that were used to play backgammon, right? There are examples of them working on things like the AcroBot. But the domains that I care about most in my lab, we tend to do